This presentation focuses on the first proof of concept developed within the MARE project, focusing on securing the ORAN architecture against internal network critical threat. This work introduces an automated security framework deployed directly within the near real-time RIC. The primary objective of this POC is to protect the near real-time RIC and its E2 nodes from critical internal attacks, such as resource exhaustion or unauthorized configuration changes caused by rogue or misconfigured xApps. To achieve this, the MARE project delivers its Iteration 1 release security functions, establishing a zero-trust AAA model inside the RIC that enforces MTLS and JWT token validation via Keycloak and Open Policy Agent. From a threat perspective, we map our scenario to the MITRE FIGHT framework, addressing initial access via trusted relationships and endpoint or network denial of service under the impact tactic. Let's look at our testbed infrastructure and scenario. Deployed on a production-ready Kubernetes cluster, we leverage Firecell's commercial dRAPS near real-time RIC platform. The defense architecture relies on Keycloak, OPA, a monitoring Prometheus stack, and a custom proxy xApp acting as our local policy enforcement point. The threat comes from an insider, a legally deployed rogue xApp that uses its valid MTLS and JWT credentials to suddenly flood the config API, simulating a textbook internal DOS attack aimed at exhausting control plane resources. To mitigate this, our technical solution introduces the DOS Protector microservice. It continually scrapes Prometheus telemetry, assesses request rates against an abuse threshold, and automatically triggers mitigation. Together with the proxy and OPA, it forms the closed-loop AAA and anomaly mitigation security function. When a request surge is detected, the DOS Protector dynamically updates OPA's deny list, forcing the proxy to instantly block subsequent rogue requests at the edge with a 403 forbidden error, aligned with the MARE PoC security component. To evaluate our framework, we track three main KPIs. First, unauthorized access rejection must maintain a strict 100% success threshold, ensuring no invalid commands pass. Second, threat detection latency should ideally remain under 100 milliseconds, with an average target below 200 milliseconds from the initial spike to edge blocking. Finally, system stability under DOS should limit RIC resource overhead to less than 20%, ensuring zero service interruption during an ongoing attack. Our implementation actions are fully completed using Python for the xApps, integrated with Firecell's dRAPS, Keycloak, OPA, and Prometheus. Preliminary findings confirm a 100% detection accuracy of flooding attempts. Crucially, the average response time from threat detection to edge blocking was measured at less than 150 milliseconds, providing seamless mitigation with zero downtime or pod restarts. The upcoming demo video will highlight this live attack injection, monitoring, and automated response loop. What happens when a 5G RIC xApp or RAN intelligent controller application turns rogue? In this proof of concept, the network sees it, decides, and shuts it down automatically. 3 xApps are deployed on the Acelerin dRAPS RIC. The proxy xApp sits in front of the config API as a policy enforcement point. The DOS Protector, or Denial of Service Protector, watches the proxy's audit metrics, and the rogue xApp acts as our stand-in for a misbehaving tenant. Every request carries a JWT, or JSON Web Token, issued by Keycloak. The proxy validates it, asks OPA, or Open Policy Agent, for an authorization decision, and records the outcome as structured audit metrics. AAA authentication, authorization, and accounting enforced on every call. We flip the switch. The rogue xApp now hammers the proxy with hundreds of authenticated requests per minute, a textbook denial of service from an authorized client. The proxy's audit counters feed the AAA dashboard live. Within seconds, the rogue's request rate punches through the abuse threshold and the DOS Protector picks it up. Watch the timeline. 1. The rogue xApp starts. 2. The DOS attack begins. 3. The DOS protector flags it. 4. It calls the AAA control plane, OPA, to deauthorize the client. 5. AAA blocks the token. Every step attributed and logged. Same token, next request 403 forbidden. The proxy refuses to forward it. The attack stops at the edge without restarting a single pod. Keycloak, OPA, and a proxy xApp together. A self-defending RIC. Closed loop AAA proven. Finally, looking ahead to future work. Technical enhancements will focus on refining our algorithms with ML-based behavioral profiling to catch stealthy, low and slow rogue behavior while expanding the testbed scale. For iteration 2, the core focus shifts to advanced conflict management. We will implement proactive E2 guidance and intent arbitration logic to resolve contradictory commands before they ever reach the RAN, while optimizing token revocation latency below 50 milliseconds, and achieving full MARE plane integration. Thank you for your attention. Please feel free to follow the MARE project on social media.